Right, okay, so it's my pleasure today to tell you about some work that I've been doing with Henry Maxfield, Alex Peach, and Simon Ross that it looks like may actually appear soon. There's a long title here, but let me explain why this is a fun talk. It's because I'm going to explain to you a very concrete sense in which the thermal field double state, we all understand quite well, or many of us do, can be used as a basic building block to construct much more interesting geometries for black holes and wormholes and so forth, at least in the context of ADS 3, which is going to be which I'm going to focus on for my entire talk. Something similar will be true in higher dimensions, but it's more complicated. For concreteness, I'm going to refer to ADS 3. So what I've written on the board here to prep things and move the talk along is the overview. Let me run through this, and then I will explain some background material and give you a proof of the relevant claims, or the outline of the proof anyway. All right, so what's the overview? Let me remind you about the thermal field double. Thermal field double is I have to call it the poster child for almost all ideas relating to geometry and entanglement. And as a brief review, Juan Maldacena explained to many of us some years ago that if you think about the thermal field double as it would be calculated, for example, by doing the conformal field theory path integral over a strip or an annulus, well, that's something that, of course, we understand that the strip corresponds to e to the minus beta h times beta over 2 here, some operator. And for simplicity, let me assume I'm working in a theory with a time reversal symmetry, so I can use it to convert broads into kets and write this as something that is a state on 2 copies of the field theory, the thermal field double state. So of course what Juan explained to us was that if I want to do this for a holographic CFT, something that has a bulk dual, there'll be a corresponding bulk path integral, which corresponds to the Euclidean path integral with boundary conditions set by this strip. I can just bend things around to draw that strip in this U shape. And that the corresponding bulk Euclidean path integral, I'm talking about Euclidean path integrals here, will, at small beta at high temperature, be dominated by a Euclidean black hole solution that I've sketched out here. And so we say that to good approximation, the approximation that I can ignore subdominant saddles in the gravitational path integral, that the bulk black hole solution is dual to this thermal field double state. Okay. Now, of course, here, this was a Euclidean story. It perhaps is useful to mention that, of course, this can be Wick-rotated to the Lorentz signature black hole. And so we think about the Lorentz signature solution as being dual to this state in the CFT. Strictly speaking, this state is time dependent. If I time translate either copy of my CFT, I get phases and the state changes. So this is describing the bulk black hole at t equals 0. 0 is nicely both real and imaginary. So the 0 slice lies in this Euclidean solution and also in the Lorentzian solution. And it has a geometry, well, a topology, which in this case is just some cylinder, which we can then discuss it later. Okay. So that was the story about the thermal field double. It was explained to many of us by Juan Maldacena and Tom Hartman that it's nice to think about this thermal field double state and this path integral construction here as a tensor network. There's some appropriate reference from earlier in history that I saw in Vidal's talk from the other day, but I wrote Juan and Tom on the board. So they had a nice story for the tensor network that corresponds to the thermal field double state. I've drawn a mutilated cartoon of it here that I should explain. Okay? So I'm going to be focusing on the high temperature limit, where if this is the corresponding path integral, so here I've just redrawn this cylinder path integral where I've unrolled it. You're supposed to identify those 2 ends. I'm focusing on the high temperature limit where this is narrow. Okay? And I want to, within each CFT copy, sort of coarse grain over scales that are fairly long compared to the thermal scale. Okay? If I do that to the tensor network in Tom's paper with Juan, there's almost nothing left. And that's because we also know holographically that if you try to compute same mutual information of a region on one, let me draw it over here, on one boundary of, say, the BTZ solution. When I compute the mutual information with a region on the other boundary, if these two are offset by more than the thermal scale, the mutual information is just 0. Okay? So if I take Tom and Juan's tensor network and I sort of coarse grain it over scales large compared to the thermal scale, there's really nothing left except lengths that go straight across. A given node, if you will, on one copy of the CFT is entangled only with what is directly opposite. Okay, great. Everybody happy with my cartoon of the thermofield double tensor network? We could put in more details, but this will make it easier to draw pictures.
What are those diagonal red lines?
They tell you that I am here interested in the CFT on a circle, and so just like here, you're supposed to identify this with this. This is a periodic tensor network. Okay. This should be identified with that or with one link over or something, but we connect them along the sides. Okay, so the basic message of my talk is that, well, tensor networks are fun things. You can stick them together in all kinds of ways. And of course, sewing together tensor networks is done by taking two copies, or you take two tensor networks, you stick them together, and you sort of trace over the things that you're merging. If you're sticking them together, you set two arguments equal, and you sum over a complete set of states. This is the same thing you do when you sew together path integrals. Okay? I'm going to use that to argue that the following two tensor networks give me essentially all of the simple three-boundary black holes in ADS3. And actually, I'll use a corresponding construction, and I'll argue to give me essentially all interesting vacuum black holes in ADS3 with arbitrary numbers of boundaries and arbitrary internal topology in this high temperature limit. Let me explain what these pictures are. This is part of the overview. I haven't told you why this is going to work yet. But what I've done here is I've taken three copies of this thermofield double tensor network that I've mutilated into this simple cartoon. There's a white copy, there's a green copy, and there's a red copy. Okay? So I've just made a new tensor network by gluing these together. This is supposed to mean that this white line is glued to that green line. This one is glued here. This is glued there. Probably I should have drawn a black dot connecting them, but I ran out of colors of chalk or I got tired. So this is what I drew. Okay. So is it clear what's happening here? There's this thermofield double network around the outside. There's one here and there's one here. 1 and 2 are connected in the middle. 2 and 3 are connected around here in this simple local way. And 1 and 3 are connected over here.
So in your blue ones, you have 2 endpoints for each edge.
I didn't draw the extra dots, but that's where...
The extra dot represents some sum over CFT states?
In here?
Yeah, the inner product of the...
Yes. If I drew a dot here, it would represent the contraction operation, which is a sum over the local qubits in the CFT state.
So it's an inner product for some discretization of the CFT. Or
the model...
Well, what are those white dots?
Well, this is a coarse grading.
Yeah.
The model represents a region of the CFT of size L much bigger than the thermal scale. Okay? So when you glue two of those together, it represents a sum over all of the states of the CFT that live in a local region.
And you're instructing me to just think about that as a Hilbert space and not worry about the details.
I am instructing you to do exactly that.
Okay.
Correct.
Is this roughly the same as saying everything is built out of bipartite kind of
Yes.
bell pair kind of?
Well, no, but
Well, they're not qubits, but
that's the claim. Yeah. So let me just mention that I have these.
isn't that claim different than what was in your previous?
Let me explain it all.
Okay.
Good. So I've drawn two diagrams. I just want to make sure I explain what these are. So this was one way to sew together three thermofield doubles to get something that has one, two, three boundaries. This is another way to sew together three thermofield doubles with three boundaries. Here's thermofield 1, Here's thermofield 2, and thermofield 3 goes all the way around like this. And the interesting thing about this version is that here we only sew together distinct boundaries, if you will. 1 goes to 2, 2 goes to 3, 1 goes to 3. But here there's a large place in the middle where I sew 3 to 3. I can do that. I can sew together tensor networks any way I like. I claim, and I will justify, that if I'm interested in describing ADS3 pair of pants wormhole geometries, things with 3 boundaries and no handles and so forth in the middle, that these are the only 2 tensor networks that are relevant in, and this is important again, the limit of high temperature. Okay? This is a high temperature story because I'm coarse grading over the thermal scale.
So don't you put these 2 short bits of 2 and 1 instead of together, and also a bit of 3 together, that will be distinct, but that will qualify one of these restrictions.
Repeat your question again, please.
So if you sort, I don't know what's the word.
Sewed? Yeah.
Sewed bits of 1 to bits of 1 and bits of 2 to bits of 2.
Uh-huh.
Just like you have on the bottom picture.
Yep.
As well as doing that on the bottom picture.
I will explain later at the end of my talk that corresponds also to making an interesting wormhole in 2 + 1 dimensions, but not those. It's one that has handles. Okay? But the basic message is going to be that you can use these thermofield doubles as tinker toys, and indeed, any interesting sewing you can do does correspond to some wormhole geometry that you can realize in the bulk.
So these aren't stationary solutions, so what does beta mean? Is it that it's stationary outside the horizon?
Let me give you a better answer.
Riemann surface.
Yeah, it's a limited moduli space of the Riemann surface. In this context, as I will explain more carefully in a moment, there are 3 horizon sizes that you can call L1, 2, and 3. And the answer is that in this context, it's sufficient to say that these are much larger than the ADS scale. So I'm talking about large black holes and corresponding limits for internal moduli when there are handles. Okay, let me stick to the case where there are no internal moduli for simplicity for a moment. Okay, so why is this interesting? Well, it's all a matter of perspective, but there are 3 messages I want people to take away. I'll state them now and justify them throughout the talk. One is that, indeed, I want to claim that the thermal field double, which we've been focused on for a long time, at least in this large black hole limit, does describe the way that very general, I will call them short connections between asymptotic regions are made. Of course, truly generic states correspond to some kind of long wormhole. That's a different story. But if you talk about short connections, thermal field double is your man. This is really, there's not much more to worry about in this kind of limit. Okay. Message 2, which goes with that, is that, as people already noticed, again, in this limit, which is effectively a high temperature limit for some sort of coarse grain description, there's very little role to be played by tripartite or multipartite entanglement. Everything is bipartite in the sense of local entanglement in the CFTs. There's a little bit hanging out here. So I didn't emphasize it in the drawing, but something funny obviously happens here where the 3 CFTs meet. Okay? So if I tried to undo my coarse graining, I would have to tell you about some kind of tripartite entanglement there. But the claim is that if I have many of these thermal size regions, the importance of this decays exponentially as I move away from this vertex, if you will.
Exponentially with what?
With the number of nodes, with the distance divided by the thermal scale. So it's a decay in distance along my field theory with a thermal length.
You aren't denying it's important if you're sitting there.
If you're sitting right there, it's certainly important. Okay? But the effect is localized and doesn't propagate. The propagation away from there is exponentially suppressed.
And is the statement that it doesn't grow with the temperature?
Also true. Does not grow with the temperature. Yeah. It remains, well, in fact, it remains localized on the thermal scale as measured in the CFT. As Lenny said, how is this consistent with claims that, for example, Alex and I made in a paper a year or so ago, or is in this paper with Bao, Nizami, Oguri, Stoika, Sully, and Walter from a few days ago, where we emphasize that there are regions of the moduli space, at least with more complicated wormholes, where you can show that there's no bipartite entanglement at all. Okay? The answer is those regions where bipartite entanglement is unimportant or absent at leading order and large n correspond to small black holes that are small compared to the ADS scale. Okay? So it's a question of two different regimes. And we noted this in the paper with Alex a year ago, but I think this really drives it home that indeed for black holes that are small compared to the ADS scale, if you try to connect a whole bunch of them.
Small means how small? It means
horizon size, small compared to the ADS scale.
Unstable black holes.
Oh, this is a microcanonical versus canonical question. Okay. What's true is that if you, in the regime where the multipartite information is critical, okay, it's difficult to realize those solutions as things defined by a simple Euclidean gravitational path integral that's sort of just geometric. You have to dress it up somehow. Okay, you have to do things that are analogous to, if you're doing just the two-boundary case, you might choose the spin structure so that you only have the Ramon sector and you don't have the Niveau-Schwarz sector. Okay. Jamie has some nice ideas about having things like that for more cases with more boundaries, but there are things that are a little tricky to write down the path integral construction of. So in the regime which is easy, where I will argue we can guess and have some control over which bulk solution dominates the Euclidean path integral, the role of multipartite entanglement is limited and localized. Great. There was a third message. What was it? This gives an infinite family of geometries when I start adding more handles and topology and such, where you can basically write down the CFT state, and you can see that the correspondence between the tensor network, if you will, and the bulk geometry is as direct as it is in the thermal field double. So that's kind of fun. All right.
Are those just other quotients of ADS?
I will explain that in one moment. Okay, now finish the overview. Now let me give the background, which will answer your question. But any other questions about the overview before I begin?
Well, eventually you will hit if you sort of make it more complicated with more wormholes, you will sort of hit these blue circles at everywhere, and then the tripartite information.
There are various limits you consider. The one in which my statements are true is the one where you fix the complication you were interested in, or you fix the topology, and then you take all of the links large. In which case, those blue things become isolated, and there's lots of room between them. Yeah. If you fix
the number of nodes, then
if you fix the number of nodes and make it very complicated, then you can make the tripartite bits relevant. But you have to work hard to do that. All right. So I will now, that was the overview, I'll now give the background and a quick proof or argument, and then give some examples. So background.
One more quick question.
Yes.
I mean, is the way that we should think of this is that if you fix the topology of your, internal geometry, and then you scale the external lengths large, the Riemann surface just becomes a strip, basically.
That's the basic point. Yep. And you have to do some scaling on, for this case, yes. That's
up to conformal factor.
That's what up. And I will make that very concrete in various ways.
So any point on one of the boundaries is close to a particular other boundary.
This is really true. This is the thing that I'll make very apparent in a moment.
Yeah. But there could be trivalent vertices where
Just
strips.
hold on.
That follows from the high temperature limit, right? That there's an Euclidean circle where.
That's the point. Exactly. It follows this high temperature limit. Hold on. The experts can just hold on. It'll all be completely manifest in a moment. All right. So the background I want to give is just to explain a little bit of the bulk geometry concerning these wormhole solutions. Okay? And it won't take long. It's not hard. I motivated this all with Euclidean path integrals. So I'm going to start with Euclidean ADS3. And actually, why do I want to start with exact ADS3? It's because, as Ted implied a minute ago, if I'm in 3 dimensions, we all know there are no local gravitons, there are no local degrees of freedom. So it turns out that if I'm looking at vacuum solutions in 3-dimensional anti-de Sitter gravity, they are all just quotients of ADS3. If I write down ADS3 and take appropriate quotients, I'm done. Good. A nice way to I'm going to restrict my attention to those quotients that give me space-times with a moment of time symmetry, because they're just a little simpler. Okay? To describe such quotients, it's useful to take ADS3, which you should think of as the Poincare ball, and I'll draw as a disk. Then there's a nice coordinate system on it, where the slice through the middle is Euclidean time 0. And then we can evolve, if you will, towards the boundary, where the boundary is Euclidean time minus infinity or plus infinity. This is just a coordinate system on the Poincare ball. And the corresponding metric is as follows. D Euclidean squared plus hyperbolic cosine squared T Euclidean times some metric on each slice. Okay. It turns out that these slices are all just, well, this is ADS3 is hyperbolic 3 space.
Isn't this Rindler slicing?
I'm in Euclidean, but it's
Yeah,
it's sort of more, it's really Milne slicing in the ball.
It's the open universe slicing.
We'll get there. We'll get there. Okay. This is the Euclidean story. Each of these slices have a geometry which is just a hyperbolic plane with a length scale, a radius of curvature that varies from something here to an enormous length scale for the curvature radius out here. That's this conformal factor you see here. So if I'm doing ADS3, you should think of this as the metric on the hyperbolic plane. Fine. Okay. Now, good. What I want to do is talk about certain quotients of this geometry. And, well, let me just consider things that I can make by taking a quotient of the hyperbolic plane, each slice, and quotienting it by some discrete group of isometries. So we take some quotient of the hyperbolic plane. I can clearly then act with the same quotient on this configuration and get a corresponding quotient of ADS3, where the t equals 0 surface is just the quotient of the hyperbolic plane that I wrote down. Good. Those are clearly solutions. This solves the Einstein equation, so the quotient does. And it's straightforward to Wick rotate these. Just replace t by it here. That turns hyperbolic cosine into cosine, and you get a Lorentzian solution. Okay? If you study those things appropriately, you will realize that they are black hole type solutions. Okay? They are, if your space here has several boundaries, which it may, there are lots of quotients of the hyperbolic plane that have multiple boundaries, for example, that one, then the corresponding black hole corresponds to a wormhole that connects, in this case, 1, 2, 3 asymptotically ADS regions. Okay? Now, it's a wormhole much like the Einstein-Rosen bridge. It collapses dynamically, because if I replace t by it, I get a cosine, so the size of the wormhole shrinks to 0 at some time. So these are not traversable wormholes, of course. They satisfy topological censorship. Okay? But nevertheless, they're analogs of the Einstein-Rosen bridge. There are a couple of special properties of these wormholes. Yes, Dave?
Why isn't this just like a cosmology, where once you rotate?
It is. The inside of a black hole is like a cosmology. So if you Wick rotate, this coordinate system does not cover the entire black hole geometry. It describes the part right in the middle of the wormhole, the thing that would have been the neck of the Einstein-Rosen bridge well, and it does not describe the ends well.
Oh, you have to continue or something to go?
Yeah, you change coordinates or continue, if you will. So what you're seeing is a feature of that this coordinate system is focused on the interior of the wormhole.
Right, but then isn't it singular at the edge of that coordinate patch?
No.
At the big, where cosine goes to 0?
It turns out no.
Because of your identifications?
It's a coordinate.
It doesn't matter. It's not singular in ADS. Let me draw a
If
picture
you
for
put it in
you.
matter perturbation, it would.
Let me draw a picture for you.
Actually-
This is Euclidean ADS.
Actually not be.
That respects the symmetry.
This is Lorentzian ADS.
He's going to draw a picture which may make it clear.
If
I
I
mean, only
wick
part-
rotate this coordinate system into a description of a patch in Lorentzian ADS, it looks like this. It does a good job at t equals 0, gets you the entire t equals 0 slice, and then it describes the interior of this light cone.
Yeah.
Great. It's clear in ADS that the boundaries of this light cone are not singular.
That's true, but then when you identify, there's a danger that they become singular.
But they're not. Trust me.
Because the identified points get close to each other.
That's right.
And that cosine goes to 0.
So they generically are not singular. There are, of course, points in the light cone that become singular that correspond to part of the black hole singularity, but most of the light cone is smooth and it's just a place in the interior of the black hole. I mean, I'm sure you believe me if I talk about BTZ, what BTZ looks like, and it's a quotient of this kind. The general story is just a more complicated version.
Do you have closed time-like curves in part of the extension beyond that region?
If you go beyond what BT and Z would have called the singularity, yes.
But I'm saying, so they just had a single, I mean, they had two ends. I guess I'm asking in the more complicated cases, do you get?
It's just like BTZ.
There were whiskers.
It's just like BTZ. Let me not distract. This is a thing for the experts. We can talk about it later. But it's just like BTZ. I swear. In fact, I wanted to mention an interesting property of this. There are only so many quotients of the hyperbolic space. And it turns out that because of that, if I look at a region of these solutions near any boundary, that solution is exactly BTZ. Okay? How big is that region? Well, it turns out, as I said, this is some collapsing wormhole, so each boundary has some corresponding event horizon. The region which is exactly BTZ reaches slightly inside each event horizon.
So that means each one is spherically symmetric?
Each one is exactly rotationally symmetric.
What do you mean slightly?
I will save questions for the experts later. I mean, if you wanted to have the global geometry of BTZ, well, clearly, the entire geometry is not BTZ. So there's, some place inside you can push that description. You have many choices in where to stop that description. My point is, there is a region that includes any given boundary and also includes the corresponding event horizon that is exactly BTZ.
Okay, but you can't go epsilon. Okay, well,
Yes.
I'll shut up.
You may go epsilon inside with the right definition of epsilon. You may go epsilon inside on the t equals 0 surface and use the corresponding domain of dependence. Okay. Where was I? Oh, yeah. So the fact that it's exactly rotationally symmetric is convenient for my outside each event horizon. It's convenient for my purpose because, in ADS space, and we're talking about duality with CFTs, we have to fuss about what conformal frame we're working in. I'm always going to use what I'm going to call the round conformal frame, where each BTZ black hole looks round. Why not? It's a convenient way to describe things. We could be more general if we like.
Wait, Don, when you say exactly BTZ, I mean, the state of the CFT is not thermal.
No, I said the geometry is exactly
But
BTZ.
the quantum state is not.
We will talk about the quantum states, we will discuss in a moment. The geometry is exactly BTZ. But the fact that geometry is exactly BTZ means that the one-point functions are exactly that of BTZ.
Yeah, this would probably be non-perturbatively small difference, but I don't know actually.
No, there is a conformal frame where the one-point functions are exactly that of BTZ.
Yeah, maybe the 2-point functions would be close, but not.
Yeah, right. But you can make the energy density completely rotationally symmetric by the right choice of conformal frame. So this is what I have in mind from the CFT point of view. All right, how am I doing? Good. Oh yes. So let me redraw this picture. I'm just about on time, believe it or not. So, as I mentioned, I'm mostly going to be interested in a CFT description of the state of my black hole solution at t equals 0. So let me focus on this t equals 0 slice, and let me just draw this picture bigger. So at t equals 0, I might have some geometry, some quotient of the hyperbolic plane that looks like this. Ta-da. All right. As was mentioned a minute ago, for each asymptotic region, there'll be a corresponding event horizon, which by time reflection symmetry has a bifurcation surface here on my t equals 0 slice. So if these are the boundaries, B1, B2, and B3, there are corresponding horizons. H1, H2, H3, where by horizons I mean the bifurcation surface thereof. Okay, great. Excellent. A useful thing to mention is that since this is exactly BTZ, or just since it is a bifurcation surface for a killing horizon, these things I've drawn are extremal surfaces, otherwise known as geodesics. So the horizons are geodesics here in this context. Okay. Now, the proof of the claims I'm making basically follows by drawing a nice picture of that. Let me explain what I want to do. So, as I mentioned, it's known since ancient times that all of these geometries can be obtained as some quotient of the hyperbolic plane, which means that I could think of this actually as some region of the hyperbolic plane with various identifications, the fundamental region for that quotient. I'm going to do something related but different. Imagine taking this pair of pants and slicing it through the middle vertically so that I cut each circle in half. There's a front piece and a back piece that I would later sew together along this seam, and that seam. Each piece could similarly be described as some region in the hyperbolic plane. I'm going to use a well-known coordinate system of the hyperbolic plane to draw you a picture of those regions. The coordinate system I'm going to use is the BTZ coordinate system. So I will remind you that the planar BTZ black hole, not the one which is the global one, but with the planar one where the BTZ, where there's no compactification, where the BTZ rotational symmetry is a translational symmetry, that thing, its t equals 0 surface is the entire hyperbolic plane. So if I want to draw a region in the hyperbolic plane, I could choose to draw it as a region of the initial data surface t equals 0 for the BTZ black hole. Let me explain to you how this works. Oh, and this is convenient for this problem because, of course, in any one of these asymptotic regions, the geometry is just BTZ. So I'm going to pick one of these regions. Let's say number 3. And I'm going to have in mind that I'm picking the one that has the largest horizon. So let me imagine that the horizons, H1, H2, and H3, have 3 lengths, which without loss of generality, I order in the following way. I want to draw this as a region of the t equals 0 BTZ solution, where in my reference BTZ solution, I make this the horizon. I'll draw the picture, it'll become clear. Okay, so here's the picture. Here is, oh, I need some colors. I have colors, good. Here is planar BTZ is often drawn in the following way. Except that I'm adding some embellishments. So planar BTZ is often thought of as a strip. Here's the strip. This is the horizon. I'm going to map the front half of this pair of pants into this problem by putting H3 along the BTZ horizon. Okay? Now, I'm only going to draw, I only need a finite piece of this strip. How much do I need? Well, okay, as I say, if I cut this in half, there are 3 seams. I'm going to call the seams, which are also geodesics in the hyperbolic plane, G13, G12, and G23. They are exactly this line, and that line. Okay. I claim that I can map this to my BTZ problem by taking a straight vertical line here to be G13, a straight vertical line here to be G23. Good. And now I need to find out what is, there's some other geodesic that is G12. I will choose 2 points here on the top boundary that I'll call x1 and x2. And of course, I can find some geodesic that connects them. It looks like that, it turns out.
But you wanted to stay away from H3.
It doesn't quite touch H3. It is a well-known fact to those of you that have studied geodesics in eta de Sitter spacetimes or in ADS black holes that when the endpoints are widely separated, the middle of the geodesic approaches exponentially close to the horizon. So I've drawn it as close. Okay. So here's what I want to point out. There's some natural BTZ coordinates, or familiar BTZ coordinates, for which the metric on BTZ looks like this. LADS squared, d rho squared, over rho squared plus some rho naught squared, plus rho squared plus rho naught squared, dx squared. Some natural BTZ coordinates, where this is the BTZ x that encodes the translational symmetry. What I've done here is to pick 3 parameters, an arbitrary location x1 for this endpoint of this geodesic. This is my geodesic G12. Another arbitrary location x2. And what's the third one? The third one is this is half the length of horizon number 3 in the BTZ coordinates. Yeah, for simplicity, just so I don't have to write things, I'm going to remove the dimensional factors. Okay. So what I've drawn you here is a picture or a class of pictures parameterized by 3 numbers: the total length, and the position of that point, the position of that point. Okay? With a little work, you can then compute the lengths of the corresponding horizons. Let me explain what I mean. This is now going to define for me something I'm going to call boundary 3. This defines boundary 1, and this defines boundary 2. Where let me again remind you that what I wish to do is take 2 copies of this picture and sew them together as the front and back sides of this. There are 2 copies of this, and I attach them by gluing together G12 in the front and back copies, G13 in the front and back copies, and G23 in the front and back copies. Okay. So out of these 3 parameters, I can generate 3 numbers corresponding to the length of the horizon 3. There's also some corresponding horizons that turn out to look something like this: H1 and H2. And the important point is that when you do the calculation, it becomes clear that these parameters, x1, x2, L3, are in 1-to-1 correspondence with the possible values of the horizon lengths. And that's good, because it's a well-known fact that these 3 numbers, L1, L2, and L3, are good coordinates on the moduli space for the pair of pants problem. So that means that my 3 coordinates here, by choosing all possible values of L3, x1, and x2, I can generate all possible pairs of pants. Okay.
Is there any significance to the fact that you've made H1 and H2 very close to H3?
I will explain in just a moment. Okay. So by varying the values of x1, x2, and x3, and L3, I can get all possible value places in moduli space. Now really, I'm only interested in this range because the rest is obtained by symmetry. Okay. I have drawn a particular case here. This picture is an accurate representation for the case when L3 minus the sum of L1 plus L2 is much bigger than the ADS scale. You can see that in the picture because here's the first horizon, here's the second horizon. Each of them more or less matches up with a piece of the third horizon, and there's stuff left over. For completeness, I should draw the contrasting case. The contrasting case turns out to be the case where L1 plus L2 minus L3 is much bigger than the ADS scale. Okay? That's the only other interesting case to draw as long as I have this ordering. And it looks like this. Blue. Blue. Oops. Dash line. It looks like that. This is H3, this is H1, and H2. Okay? The important thing to take away from this picture, the thing we explain, is that in the limit where this becomes very small on my picture, it's receding to the ADS boundary, where of course space is enormously large. And so as this shrinks to 0, there's an enormous portion of H1 and H2 that are in fact almost coincident here. Okay. So if I step back and give you some space, and if you stare at these pictures long enough, you'll realize that this is the same kind of picture topologically as this one. And that one's related to that one. Okay? Let me explain that pictorial connection before I say why they're actually causally related. Here you see there's a region near boundary 1 that includes this horizon that has been sewn to this collar down here around boundary 3. Okay? And as I mentioned, geodesics in hydraulic space or in the BTZ black hole tend to approach each other exponentially. So this separation that I've drawn here is really exponentially small. So essentially, this is sticking a copy of BTZ to a copy of BTZ here. The same is true over here. The interesting thing is what happens in the middle. What happens in the middle is you sew this whole front panel to a corresponding back panel by identifying this geodesic with its image on the back guy, which means you're sewing this collar near boundary 3 to a corresponding collar, piece of a collar, near the back part of boundary 3. You're sewing them over this connection here. So that's this here. So this is really what this geometry looks like. This picture shows what the geometry looks like. If you're in the middle of boundary 3, but at, say, 0 and pi, by far the shortest way to get from here to here is just go straight through here and not go anywhere near 1 or 2. Okay. Good. Well, I'm basically done, which is good because I'm out of time. Let me explain the argument of why these things are logically connected, having shown you how the pictures work together. Okay. So what you might like to do, well, let's go back here. I gave you a Euclidean geometry. It has some Euclidean boundary, which, up to a conformal factor, is the same as the geometry that t equals 0 surface, because the solutions that I have, different Euclidean times, differ just by an overall scale factor. So, if I wanted to do a bulk path integral with boundary conditions set by this surface, that must be dual to a CFT path integral. That, since it's a CFT, I could think of as the CFT path integral over my t equals 0 surface. Logically speaking, it's the path integral over what would have been the t equals minus infinity surface, but they're conformally related. Okay. So I've just described those geometries. And I'd now like to do the CFT path integral over the Riemann surface given by gluing together two copies of this in the way I described. Well, there's a piece of this geometry which is conformal to the cylinder because it's a piece of BTZ. So if you do the path integral on that, you get the thermal field double. Another piece which is a similar color that gives me a cylinder that gives me a thermal field double. And the same here. And what you see is what the path integral tells me to do is take those three pieces and sew them together with a little thing inserted in the middle. Okay. So what does the thing in the middle look like? Well, I'm working in the limit where all of these horizons are large. Let me just draw you the picture for the infinite L case, where they're all strictly infinite. Then this is the well-known piece of the hyperbolic plane, which has cusps on the end and has some finite area, and which has exponentially thin edges, which I've drawn very poorly. Those are only polynomially thin at most, but they're supposed to be exponentially thin. Okay? So, if you're doing the CFT path integral over this, it's some kind of, well, it's a thing that allows you to stick three states together, but what is it? Well, out here, where the thing is exponentially thin, it should be, I claim it's fairly obvious, I will give a longer argument to those who wish to stay later and ask questions, that it is just thinking of it as an operator between a state here and a state here. This is just the identity operator up to exponentially small corrections. So thought of as a tensor network, it's the empty tensor network up to exponentially small corrections far up this line. And similarly here and here, and there's something left in the middle.
Wait, empty means, what is empty?
It's the identity. Identity operator. It's the identity operator.
Is that just the thing on the
it's
white
actually,
lines and the white line?
it's actually in this picture, no, this is supposed to be the thermal field double, so it's slightly non-trivial. It has a temperature in it.
But it's close to it.
This is the infinite temperature version of that. And it's the thing which I haven't drawn that links them in the middle.
Yeah.
Actually, it's, yeah, okay. So really, the correct picture is that this thing that has tripartite stuff has some little thin tail that comes over here, but it's exponentially small.
But identity operators, you mean you have EPR pairs across, like diagonally across through the cut. You don't have product states. That's what's confusing with the.
Okay. If I think of this, if I think of the piece up here as an operator that maps one side to the other, it's the identity operator. If I think about it as a state, it's the maximally entangled state. And I really mean the maximally entangled state. I mean, what it really is locally, it's a thermal field double at exponentially high temperature.
Right.
A much higher temperature than I started with. Okay. So that justifies these pictures. That's what I've drawn. Okay. So the CFT path integral that you would most naturally associate with these bulk geometries gives exactly these guys here. What I haven't yet argued is that that's actually dual to the bulk geometry I've discussed, meaning I haven't actually argued that this is the bulk geometry that dominates the corresponding bulk path integral. Okay?
You haven't? Really?
I haven't explicitly argued that. It's natural for several reasons. One, we're in this high temperature limit where you expect things to be pretty easy. The other is that because it's just pieces of BTZ pasted together, I could do any Ryu-Takenagi, or actually Hubei-Rangamani-Takenagi calculation, okay? And it would give this answer. All right? Furthermore, at least with Tom over there can maybe help me rule out cases I don't understand. They're non-handle body possible saddles. But if I ignore non-handle bodies, you can prove that no other handle body could possibly match this pattern of entanglement. So this must be the dominant saddle. So that's my argument. So I claim that these bulk spacetimes in this limit are dual to these pictures. That's my basic message. I'm 5 minutes over time, so I should stop here. But my next thing I would have done is to just draw some pictures of fun other examples for those that are interested. So thank you very much.
let me propose a computation that might be hard, but interesting.
Mhm.
So let's take the pair of pants.
Yeah.
That defines a state in the threefold tensor product Hilbert space.
Mhm.
And there's a measure on the moduli space of pairs of pants.
Yep.
And so that defines a probability measure on the space of states that you construct in this way. And so for some definition of what you mean by a state having only locally bipartite entanglement, you could calculate the probability that a state has only bipartite entanglement as opposed to the probability that a state has multipartite entanglement.
Okay.
And so you could compare this to the kind of following toy computation where you consider a state of 3 qubits.
And remind me that if you're just doing the classical moduli space in the pair of pants, its total volume in moduli space is finite or infinite?
It's finite.
Good.
For finite L1, L2, L3, it's finite. It's a number. That's a function of L1, L2, L3.
Yeah, but what about when you integrate over L1, L2, L3? Because that's the interesting question. If we fix L1, L2, and L3, there's only one geometry to discuss. We'll put some cutoffs on it.
I don't know what precise. I don't remember what the form. It's
Yeah,
a polynomial in L1. So the volume of the moduli space is a polynomial in L1, L2, L3.
Yeah.
You might have to put a cutoff on it.
Yeah.
Okay. Yeah. But you could imagine taking 3 qubits and
Yeah.
putting the Haar measure on the space of states. And for some definition of what you mean by only having bipartite entanglement, calculating the probability that the state has only bipartite entanglement and comparing it to the calculation that you did in the bulk.
Yeah, I'm not sure that's very interesting, just because there's a large region of phase space, and the one where this dominates, where the Hilbert space on each side, or the entropy of each side, is enormous.
Wait, what does it mean, 3 qubits with only bipartite entanglement? 2 of them are entangled, the third one has to be left off. And,
That's what it means.
That's what it means.
That's what it means.
Or some linear combination thereof. Right. Okay. So I think that it's...
I mean, qubits might not be very as interesting as systems with large
They're-
Hilbert space.
Yeah.
What is the density matrix of the individual black holes? Is it pure thermal or not?
No.
Okay. It's not quite.
They're exponentially small.
In this context,
No.
it's pure thermal. In this context, you'll see that boundary 3 has a non-trivial connection with itself, and so it's not thermal. Which, of course, is clearly true because if you use HRT in this context, there's mutual information there. Boundary 3 has much less HRT entropy than its thermodynamic entropy.
But in the first case, it's pure thermal?
Yeah, up to some possible exponentially small correction.
Oh, okay.
I have to think about that, but it's basically, well, it's a question of what you mean. As I say, the geometry in the bulk in each color region is exactly BTZ. So if we normalize things by the corresponding energy of the BTZ black hole and do an HRT calculation, then you'll find that the entropy is given by the thermal answer. It's the same as BTZ.
That's sure.
Can't you just say, like, if you look at a 2-point function, then it's almost, then in the Euclidean picture, then
Yes.
it's almost thermal, except there are these geodesics that go the long way around, which give you exponentially small corrections.
You may also say that.
Yeah.
You may also say that if you're interested in 2-point functions of light operators, sure.
Yeah, that's just a way to see the size of the correction. So it comes from that kind of thing.
Yeah.
This seems really related to an old paper by Skenderis and Van Ries.
Yeah, sure.
Is it, of course, they didn't mention tensor networks.
Right.
But in what sense does this, add something to what they said, or what did they leave out? Or
Well, it gives you, it's a more specific understanding of what's happening and a specific formula, if you will, for the dual CFT state in a arguably useful manner, which is valid in this high temperature limit where things simplify. The basic story, I should apologize if my summary of the history was too brief, the basic story about these kinds of wormholes being dual to CFT states given by path integrals over Riemann surfaces, that was certainly known long before what we did. For example, Skenderis and Van Ries talked about it. Juan Maldacena, in his Eternal Black Hole paper from 2000, was it 2 or something, also mentioned it. Okay, so that's ancient knowledge. This is just extracting a more concrete description in this high temperature limit.
But I was just, while you were talking, I looked up to see what it was they claimed.
Yes.
They were saying that they could identify in the CFT state the parameters that characterize.
Yes, but they're wrong. Well, I'll talk about that later. You and I can discuss that offline. They wanted to do something with one-point functions that is a confusion about conformal frames, but we'll discuss that.
So then coming to what you did, you said you have a...
Function, no, sure.
Wait, are these pictures recipes for actually writing down in detail what the CFT state is?
Yes, where in detail means what I said. It's good to describe the CFT state exponentially well away from these places.
Is there anything that you can say about the center of this and the tripartite entanglement, or is that just beyond anything?
That's beyond what we have to say now, but obviously it's a very interesting thing to investigate, right? Yeah. Oh, sorry, there is one thing I can say, which I should say, and I should have said. This story about tripartite information being localized in regions and suppressed elsewhere also showed up in the paper that Dan and John Preskill wrote and in their model. Okay. And Ben, I'm sorry, yes, and I don't know who else is here, okay? They were considering something that is effectively setting these all approximately equal to LADS. It turns out it's that kind of thing. But as is often the case, there are sort of sharp phase transitions in this business, and if you're around order 1, it can be like the high temperature limit, okay? And in fact, so they have a definite model for what this vertex, if you will, this trivalent vertex, you glue things together, would look like in that particular case.
We actually had both of the regions, both of the phases.
Both of the phases.
Both of these two pictures.
You probably did. Good. Right. So there's this parallels there because you would have considered all possible kinds of regions on the boundary.
Yeah. So
yes.
There's this cross ratio, and in one
yes.
limit it looks like the bottom, and the other limit it looks like the top.
That's right. You would have done it with 4 instead of 3.
With 4 boundary intervals. Yeah.
Exactly. So for what we know or conjecture about that, I would refer you to their paper. Mm-hmm. That's the right place to study it. Yeah. Dan.
Yeah, can you comment at all on the time evolution of these states or the perturbations there, and does it work like the standard two-sided case?
So I can tell you about the classical GR unperturbed geometry, and there it basically works like the two-sided case.
So it gets longer in the way you...
Yeah, it turns out that's implied by the statement I made to Alex a bit ago, that there's a region near each horizon that's exactly BTZ. And so as you know, at late times, that's going to dominate, and you get the standard kind of evolution. Yeah.
And what about perturbations?
I haven't studied it. Be fun to do so. Yeah. All right, Alex and I have some plan to study similar things just at t equals 0. Let's see what happens.
The last question.
So from the tensor network picture,
yeah.
you could have a possibility that you have a non-planar structure, but from
yes.
the BTZ quotient, sorry, the ADS-B quotient picture,
yeah.
you can always draw all the possibilities on just a quotient of a H on the hyperbolic plane.
No, you can draw all the possibilities as polygons in the hyperbolic plane where you give rules about what to identify. In the same way,
so that would recover a non-planar.
Yeah, you can make non-planar things. So this is the message that I would have given if I had more time to draw examples. You can really glue these things any way you want, and there's some corresponding wormhole. In particular, a fun class of things to consider are those objects with one boundary, one asymptotic region, and complicated internal topology, arbitrary numbers of handles. And this gives you a prescription for how to write down the tensor networks, again, up to the same lack of knowledge about these little bits here, that tell you what the dual CFT state is. So that seems like a fun arena for future exploration. And of course you do that with more boundaries as well. I should mention that more fun happens if you take 2 pairs of pants. And of course, everyone in this room, I think, knows that you can take 2 pairs of pants and you can glue them together into a 4-boundary object. Okay? So what is that here? You take 2 copies of one of these guys and you glue them together, okay? And of course, you know that when you do this, there's a new modulus that comes in, which is the relative twist, okay? It's a fun fact that especially if you take 2 copies of this guy and glue them together with a twist, the pattern of entanglements you get between the resulting 4 boundaries displays chaotic behavior, okay? If you have some sort of irrational multiple of 2 pi, which is your twist, you will find that a given boundary has one piece entangled with that boundary, another little piece maybe with that boundary, another one with this boundary in some kind of fractal-like structure in general. So you can do all kinds of interesting things there. All right.
Okay.
Thank you very
Thanks
much.
very much.